excited to be here today because I'm going to tell you about my main result in my PhD, what we cannot learn with bounded memory. So a bit of a warning before I start. My PhD is very theoretical, practical, so it's going to be a bit different from the usual meetup. So you won't see a lot of cool graphs, but I promise you that you will see a lot of cool mathematical ideas. Okay, so ready to start? Machine learning. What is the vision? So the idea is that we have a lot of data. Google have a lot of data. Booking.com have a lot of data. And what we want to do is to create learning algorithms that utilize this huge amount of data in order to answer all sorts of questions. For example, to predict if someone will have cancer, or where someone would like to travel to, and many different tasks. And nowadays, learning algorithms seems like they can do everything. Like they're magicians that can answer every question. But now I'm gonna talk about the downside, about the limitation, about what learning algorithms cannot do, and how I'm gonna do it. So I'm gonna focus on one natural constraint, the constraint on the memory. I'm gonna show that if the learning algorithm has bounded memory, then it cannot do things. Okay, so before I start, I want to give you some motivation of why looking on space is important. So why should we care about bounded memory computation? So first of all, this is a natural question. We care about machine learning that are running fast. And the next step, after considering time, is looking on the space. So this is one motivation to consider this question. But there are other motivations. A second one is that, as we said, as we all know, we are living in the middle of the big data. We have a lot of data. So we cannot expect our learning algorithm to remember all the data while training. Another reason is that neural networks. Who heard about neural network here? I thought I would see much more hands. So there is a lot of buzz on deep neural networks, and actually they can be viewed as bounded memory algorithm because at each step they just remember the current hypothesis, the current weights, and they change it a bit. And another reason, the neural network that is over here, our brain, is also bounded memory. So it's really interesting to understand what we cannot do. Okay, so I hope that you're motivated enough, and let's get started. So what is our plan for today? I'm going to start with some definitions. I'm going to define what is PAC Learning. I'm going to talk about online learning, which is obviously our topic of the day. Then I will discuss what is bounded memory learning. I will formulate the problem, and then I will tell you about the main theorem and a surprising conclusion. Okay, so supervised learning. What do we do in this framework? We have a lot of labeled examples, and we want to answer some questions. So, for example, let's say that we want to get an image and say whether there is a cute cat or not, because we want to know whether to send it in an email to a friend. So we get a lot of images of cats and not cats, and then we are starting to think about an hypothesis. And then I think, I know, it must be the pointy ears, because all the cats here has pointy ears and the dog doesn't. And then it will think about an hypothesis, and this is what it's going to return. So this is supervised learning, getting a lot of examples and returning hypotheses. Let's be a bit more formal. So to formalize it, we are using the notion of PAC Learning. It was invented in 1984 by Valiant, and he said the following. When we have a hypothesis class, so hypothesis class is simply a set of possible explanations of the data, which means a set of functions from the examples to labels. So our learning algorithm gets a lot of data that is labeled by some hypothesis in the class. And then our learning algorithm should answer some question and should return some hypothesis. But how can we tell if some hypothesis is correct or not? So what we would like is to return an hypothesis which is close to the correct one. So again, what we want in PAC Learnable is that no matter how the examples are chosen and no matter how they labeled, we want to find some learning algorithm that will return a hypothesis that is going to be correct on most examples that we will see later. Any questions about it? Okay, so let's move on to the next definition. Online learning. So in online learning, what we have is our examples are given to us one by one. And at each step, we need to give an hypothesis. And we don't see all the examples at once. So let's return to our cat example. We want to know whether an image is a cat or not. And we are given some picture, and then we need to say what is our hypothesis. For example, we think that a white object is a cat. And then we get some new image, and then we say, this thing is the middle, is a white object, so it must be a cat. And then we are wrong. We get a new label, and the number of mistakes we are doing is increased by 1. So, and then we need to get to return another hypothesis. Let's say if our hypothesis is if there is a tail, this must be a cat. So we get another image, and then we don't see a tail, so we say it's not a cat. But we are wrong, and our number of mistakes is up again. And then we have another hypothesis, and again we label it, and so on. So let's be a bit more formal. What is the online learning framework that we have just seen? So we are getting examples one by one, and after each example is given, we are supposed to return some label to it. Then someone tells us what is the correct label. And the goal, obviously, is to minimize the number of mistakes that we are doing. Okay, so this is online learning. Any questions about it? Okay, so let's move on to the third definition, which is online learning with bounded memory. And we are still with the same example of predicting whether an image is a cat or not, and now what's going on is the following. We get an example, we return a hypothesis just like before, but then when we answer some hypothesis, we forget everything. We can't remember all the examples that we've seen. So now that we want to hypothesize and give some new hypotheses, then we just need to do it without looking at all the examples. And this thing can be much harder. So the question is, what cannot be learned with bounded memory? Okay, so let's define. So now I'm getting into like the details of it. What is learning with bounded memory? So one thing you need to know about me, I really like graphs and I like looking at things as graphs. So let's think about the algorithm as a graph. So if we have some algorithm, how can we present it as a graph? So we can just take a look at the memory that the algorithm can be in. So if there are b bits, there are 2 to the b possible memory states that the algorithm can be in. Okay, and then from each memory state, we are going to get a labeled example. And then the algorithm is going to change to something else and return some hypothesis. And so on and so on and so on. This is a bounded memory algorithm. And so, since we are working on the difficult part of what cannot be learned, we are allowed to do some relaxations. So we are going to allow the algorithm not to return an hypothesis after each step. Okay, so on this axis is the memory states, and this axis is the number of examples. Let's just make sure that we understand this concept. What I've described right now is a way to look on the entire algorithm as a graph. How is one run of the algorithm is going to look like? So at the beginning, we're going to start in some memory state. Then we'll get some random labeled example, and we will continue in this way. And we will end up in some hypothesis and some vertex at the end. So one run of the algorithm simply means one path in this graph. Okay? Okay, so let's try and understand what we do know about this question. And let's try and design some algorithm and find out what are their parameters. So think about the most simple algorithm. The one that just remember all the examples that he saw. So this algorithm is going to assume that at the beginning, all the hypotheses are possible. Then it's going to get some example. Now, all the hypotheses that are consistent with the example is something smaller. So we can just throw away all the examples, all the other hypotheses, all the thing in black, we don't care about it. We just care about the hypothesis in green. And then we are going to get another example. And the set of hypotheses that are consistent with both examples is reduced. And again, we will continue in this way until we're going to get to some small subset of hypotheses. Then we'll say, we know the answer. Okay, this is one simple algorithm. Let's analyze it. So, how many examples do we need? So, if we will think about it a bit, we'll see that we need about log age examples, because at each step we just throw away about half a constant fraction of the hypothesis set. So after about log age examples, we'll have the correct hypothesis, which is close to the correct one. But how many memory bits this algorithm uses? So in order to have this algorithm, we have a few ways to implement it. One way we can have age bits, and just to denote for each hypothesis whether it's in our green settled. Another way is remember all the examples that we've seen so far. So this algorithm uses a small number of examples, but a lot of memory bits. Okay, this is one algorithm. Let's move on to another. Here's an algorithm that begins with just ordering all the hypotheses in some arbitrary way. Then, at the beginning, it tests whether the first hypothesis is close to being the correct one or not. So, if we will think about it, checking whether one specific hypothesis is close to being the correct one is pretty easy. We just take new examples and check whether it's consistent or not. So we're going to test whether the first hypothesis is close to being the correct one or not. If it's not, then we'll just move on to the next hypothesis, and the next hypothesis, and so on, until we will find some good hypothesis. Okay, this is one nice algorithm. Let's analyze its parameter. So, if you will notice, we will, in the worst case, maybe an hypothesis which is close to the correct one is the last one. So we must use about age examples, which is pretty bad. But hey, the good thing about it is that we just need to use about log age memory bits, just in the index of the correct hypothesis, which is really small, the smallest thing. Okay, great. So let's put what we have in one table. So in this table, a point is going to be an algorithm. And an algorithm for us has two parameters, the number of bits that it uses and the number of examples. Okay, so the algorithm that we just saw, we said that the number of bits that it's using is log age, just remember the index of it. But the number of examples is age. Notice that we can't do anything better than log age at the worst case. We must be able to just write the index of the answer. But if you want something to use more bits, no problem with that. Okay, the next algorithm uses a small number of examples, only log age. So notice the difference between age and log age. It's exponentially larger. And we cannot hope to have something better than log age. But if you want to use more examples, no problem. So when you look on this table, what do you think? So immediately what we can ask ourselves is, what's going on here in the white square? Is everything over here is green? Maybe we can do, and maybe we can have an algorithm that uses about log age memory bits and about log age examples. Maybe everything in here is red, which means we cannot do better than what we just saw. Maybe it's a mix of everything. So this is what I was interested in, understanding what's going on in here, in this white square. So this question, Rachel from the Valiant Institute asked me, and it was also asked by a paper from my group from Stanford, and they wanted to understand what's going on in here. And this group from Stanford asked this question for one specific class. They wanted to know whether learning parities. So it's not important now exactly what parities is, just that it is known to be hard in several cases. So they conjectured that indeed parities is going to be hard also for bounded memory. And indeed, Ranraz was able to prove that the problem of parities is difficult in bounded memory. He proved a very strong lower bound. He proved that we must use at least log age times log x memory bits, or about age examples. But this result is only for one specific class of parities. And what I wanted to know is what's going on in the general case. So how can we prove lower bounds for general hypothesis class? Okay, so I want to tell you about my answer, but before that, I will introduce one more graph, which is the hypothesis graph. So let's think of a way to take an hypothesis class and consider it as a graph. Okay, so what are the components of an hypothesis graph? So the components are hypothesis, obviously, and examples. And what is the connection between an hypothesis and an example? So if the example is consistent on this labeled example, which means an example and its label, then we will have an edge between them. Okay, so this view is nice, but the cool thing about this view is when viewing hypothesis class as graph enables us to take ideas from graph theory and utilize it to our case. So specifically, the concept that I'm taking from graph theory is mixing. So mixing is a way to understand whether a graph is close to being random or not close to being random. Okay, just a bit of a warning. So now checking whether a graph is close to being random or not, but if you care about the details, so listen to this slide. Okay, so how can we tell if some graph is close to random or not? So first of all, there is the notion of density. Density just means the fraction of edges in a graph, which is a different way to think about it is simply take two random vertices. What is the probability that between them we will see an edge? This is the density. Okay, so if we have a random graph, what is the number of edges between them? So the number of edges between two subsets, S and T, the expected number of edges is going to be the maximum number of edges, which is S times T, times the probability to see an edge, which is exactly P times S times T. So this a graph is going to be close to random if this difference is small. And this is a way to formalize it. We have some parameter that controls how random this graph is. So if D is small, it's going to be close to random, and if D is large, it's going to be far from random.
Could you maybe explain what you mean by a random graph in this particular setting?
I'm just taking a graph, and I'm saying that if we have a random graph, just means an edge, like take every edge with some probability P. Thank you for the question, and you're welcome to ask others if you have. Okay, so some examples of mixing graph. So parities, the problem that I told you that is known to be hard, is actually a really good mixing graph. It's really close to being random. And another nice thing is if you will take a graph, it most likely is going to be a mixing graph, a really good mixing graph.
And good mixing means it's hard to learn?
You will see in a second. Okay, so our theorem. So our theorem connects mixing and learning. So here's our theorem. It says that if a hypothesis graph, if a class is mixing, is a good mixing graph, then either we will need many memory bits or we will need many examples. So basically, if a graph is mixing, we cannot learn it with bounded memory. We will need exponentially larger examples from the basic algorithm that only used log-age examples. So actually what we have is some sufficient condition to show that some problem is hard to learn with bounded memory. And another thing that I like about this one is that we have some combinatorial framework to prove hardness for bounded memory algorithm. I'm not going to show you all the details of the framework, I'm just going to show you a little bit, and I hope you will be excited as I am about it. Okay, so what we have on this table. So basically what we proved that all classes that are mixing are hard to learn, so this square is red mostly. This result was also proved in parallel with us, independently by Ranraz, and he used some algebraic notion of mixing, and we used a more combinatorial one. Okay, so the framework that I promised you. One of the main notions that we introduced is certainty. We want to measure how certain our learning algorithm is in its answer. So how can we define how certain an algorithm is? So maybe let's start with examining how certain a specific memory state is in its answer. So what we have is, for each memory state, we have some probability distribution over all the hypotheses, and this distribution denotes what is the probability the correct hypothesis is some age given the algorithm reached a memory state. Okay, so let's see if we understand this concept. If the memory state is completely certain of its answer, he knows that the correct hypothesis is the first one, how this probability distribution is going to look like. So in this case, we will have a delta function, because the probability of the first hypothesis is going to be very high and all the rest is going to be small. And how this distribution is going to look like in the low certainty case. If a memory state completely clueless about what is the correct hypothesis, so how this distribution is going to look like? Exactly, yeah. This is a uniform distribution. Okay, so great. We have defined how certain a memory is. So we understood how this distribution is going to look like, but we wanted one measure to know how certain a memory state is. So what we can do is just check what is the distance to a uniform distribution. So we said that if it's uniform, it's very uncertain, and if it's far from uniform, it's a delta function, it's certain. So there are many ways to define distance between two distributions. One way is the L2 square, and this is what we've defined. Okay, and now we wanted to know how certain the algorithm is in its answer. So we'll just take the average certainty over all the memories. Okay, so this is our main notion, and I want to show you how, given this notion, we have done. So what is that? At the beginning, before the learning algorithms didn't get any examples, the certainty is extremely low. It doesn't know what the correct answer is. But at the end, after the algorithm worked so hard to learn what is the correct hypothesis, the certainty must be huge. It must be some constant. What we will show is that the certainty cannot increase by much if the memory is bounded. If we have this, we are practically done because we said that the certainty is low at the beginning. Certainty must be high at the end. At each step is going to be really not increasing by much, so the number of steps must be huge until it ends. The proof outline is clear. So now it's not clear how I'm showing this, how can I tell that the certainty is not increasing by much at each step? Okay, so I can't give you all the details because it's a 51 pages proof, but let me give you some of the intuition. Okay, so if we have a new example, what the algorithm can do about it? So basically it has two things it can do. Either it can remember only a little bit about the current example. Remember, it doesn't have a lot of memory, so it cannot just remember everything. So this is one thing that it can do, just remember a little bit. Another thing you can do is remember the example in detail, but you must forget many things in order to do it. Actually, what we proved that indeed any learning algorithm at each step must do basically one of those two things. Okay, so what we can do about it? How can we show that the certainty will not increase by much in this case? So let's just focus on the first case. On the case that we don't really remember the example in detail. So in this case, for classes that are mixing, classes that are close to being random, there is some principle, the forget some lose all principle, which basically means that if you are giving up, if you just remember a small amount of knowledge about the example, then you're screwed. You didn't learn a lot. So this can be viewed as mixing because what we only know, if we just remember a little bit from the example, is that the example must be from a large subset. But if we only know that the example is from some large subset, then we haven't learned anything. The distribution over all the hypotheses is going to be close to random. And this follows from the mixing problem. So this is the idea of why it's hard to learn with bounded memory. Okay, so I promised you a surprising conclusion at the end. So we said that most problems are mixing. And we said that mixing are hard to learn with bounded memory. So this means that most problems are hard to learn with bounded memory. But it's very surprising because neural network seems to learn everything. So how can it be? So my guess is that luckily for us, real-life problems have a lot of structure. And if some problems have structure in it, they are not so close to being random. And this is why they might be able to be learned with bounded memory. And this is it. Thank you. Yeah.
I think there's an article that tries to explain why neural networks do a good job on, for example,
there are many papers.
Yes. Trying to give a concise explanation that most images are either symmetric or they behave the same whether you move them or not, and isotropic, and most natural problems behave like this, and this is what neural networks have been proven to work on the class of inputs that have these attributes, so this is why they are good.
Yeah, I completely agree. So, whoever heard about convolutional neural network, for example, use exactly that. They are using the fact that if we will they are symmetric to translation. If we were moving the picture a little bit, the answer is not changing. And this is the reason that convolutional neural networks work so well. So I completely agree. Yeah.
So if you're approaching to a new problem, can you tell in advance if it's easy to learn it, hard to learn it?
So this line of research is the beginning. There are many open problems, and one really important open problem is to take it and check it and use it more empirically. But it's just the beginning, so you're welcome to join the effort.
So you could check the mixing. I mean, if you have a set of hypotheses, you could try to make a sample of the hypothesis and have examples of the output and check the mixing.
Yeah, but the problem a bit with this approach is that it's hard to check locally this concept of mixing.
That's actually what I was curious about as well. So this mixing is really nice in terms of like if you have a discrete set of hypotheses, then this notion of the graph that you're drawing makes a lot of sense. But my mind just, I tied myself into a knot when I was trying to think like, okay, so how do you then do that for continuous hypothesis classes?
It's also a very interesting question how to take these ideas to the more realistic situation of discrete case. Again, this is just the beginning, so you're also welcome. Yeah.
Do the results change when you change the notion of certainty
In what way do you want to change it?
I don't know, use like entropy instead of difference from the uniform.
So, it's a good question. The reason that we use the L2 square norm is basically just because it worked. We'll need to check whether...
Proof for a general case of like the hardness for the general case, but you don't like look at specific types of problems and subsets in for instance, in the parities, like a specific subset that might be solved easily, right? Or like you show that in the general case, these problems cannot be solved easily, but what about like specific instances of problems?
So what you're saying maybe, so if a class is mixing, the subset of it is also going to be mixing. So also a subset is hard.
Could you probably give a simple example of a question which you want to answer but cannot learn because it's missing?
Parities?
Parities is not something you want to answer. It's something which
From my life?
From everyone's life.
So,
science practice.
this is what I claim at the end, that but I think that the problems in real life are very structured. And this is why it's not going to be mixing. But I think it's very important to understand the limits of what cannot be solved. We need to understand what we cannot do in order to understand what we can. Any more questions? Alright, so thanks.